Great. So, yeah. So the MRIT sequence design traditionally rely on vendor-specific programming environments as we see today. Despite giving obviously the best performance in terms of sequence customizability, these are difficult to master and do not allow for portability across different vendors. Open source alternatives, on the other hand, enable fast prototyping and portability, but typically allow limited prescription time modification of sequence parameters, such as the matrix size, the resolution, and timing. The goal of this work was to bridge this gap, enabling prescription time sequence design using a vendor agnostic framework. And we choose Pulseq as it is the currently most popular open source sequence design framework available. To achieve this goal, we proposed a TCP/IP client-server architecture. In its setup, the user will set the imaging parameter from the standard scanner user interface as for any other vendor-provided sequence. The sequence process on the scanner will then basically act as a client, communicating the design routine name and the imaging parameters to a server and waiting for the sequence object. The servers will receive the input, execute the requested Pulseq-based design routine with the specified parameters, and return the sequence object to the scanner. The server app can be executed on an external machine, such as server or cloud computing instance, or directly as a separate process on the scanner. The main requirement for the server is to provide low latency, as the sequence must be readily available on the scanner once the user sets the desired parameter on the interface. In this perspective, the use of Pulseq presents certain challenges. This is because Pulseq specification, while straightforward and easy to read, represent the MRIT sequence as a sequential list of blocks defined as a set of simultaneous RF, gradient, and ADC events, without enforcing a periodic structure such as sequence TR. These do not translate well to every vendor-specific hardware representation, such as GE Healthcare, for instance, which might rely on this periodicity to reduce memory allocations and requiring a time-consuming conversion step. To overcome this issue, we propose an additional abstraction layer of the Pulseq specification. In our representation, a sequence consists of a typically small number of base Pulseq blocks, which are organized in segments, and a dynamic loop table. Each segment is an ordered set of base Pulseq blocks representing a periodic block pattern in the sequence, such as a single TR. And the loop table will contain the dynamic sequence parameters, such as the scaling and the phase of the individual waveforms included in the blocks. In practice, we implemented a builded pattern relying on this representation to either construct a native Pulseq sequence object or different vendor-specific structure, for instance, for a GE Healthcare interpreter, and skipping the conversion step and reducing the latency. As a proof of concept, we integrated this workflow on the GE Pulseq interpreter. Here, as you can see, the user interface is exactly the same as a native sequence. The user interface buttons, as well as the actual design routine that is called, can be enabled or disabled according to a text-based configuration file, which can be selected the runtime from the UI itself without requiring a compilation of the interpreter. Using this framework, we were able to successfully modify on the fly the field of view, matrix size, and echo time of a 2D gradient echo sequence directly from the scanner, as you can see from this figure. In conclusion, we achieved prescription time design of Pulseq sequences with similar latency as the native sequence without requiring any external hardware. And as a future work, we'll aim to extend this approach to other interpreters for other vendors and implement vendor-agnostic online reconstruction, example via Gadgetron as well. Thank you for watching.